about where do black holes hide in a quantum collision. So this is research funded by ANRF. And this webinar is part of the National Webinar Competition 2026 organized by ANRF and IIT Mandi. And this is based on an upcoming work titled Bootstrapping Black Holes at Low Impact Parameters, done in collaboration with Professor Anindya Sinha from ISC Bangalore. And I am Diptarka from IIT Kanpur. So first of all, we are all familiar with stars. And we see them every day. And stars, it turns out that if they get too massive, then they collapse. They start collapsing, they form more and more dense objects, and then finally, they form black holes. And black holes are predictions of Einstein's theory of general relativity, which is wildly successful. It has applications in GPS, and it can predict things like the movement of Mercury very, very accurately. And Einstein's theory also predicts that there are something called gravity waves, which objects of strong gravity, like a black hole, will emit. And these gravity waves are waves in space and time. So they stretch and pull space and time as they cross. And they're very real. So this signal of gravity waves from a black hole, in fact, two black holes, which were going around each other, a merger that took place 1.3 billion years ago, was observed and detected in Earth in 2015. So I'll come and tell you more about that. However, there has been a puzzle since 1970s about black holes, which is the fact that black holes are not really black, so they radiate, so they have temperature. And this is what Stephen Hawking showed us. And it means black holes follow laws of thermodynamics because they have temperature, and we can actually make predictions using these laws of thermodynamics about black holes, about classical predictions about black holes. However, in order to have this temperature, the radiation that needs to come out of the black hole is quantum. And this is a place of contact of Einstein's theory of general relativity and quantum mechanics. Quantum mechanics is also a wildly successful theory, and it has renowned success, especially in context of particle physics, where you take particles, high energy quanta, and you scatter them. And what comes out, you measure them, and because it's a quantum mechanical theory, what you measure are probability distributions. So you measure how much energy comes out if you scatter, and then you measure, you put your detector in some angle. Okay, how much energy comes out with what probability? Okay, now going back to black holes, I told you that they were detected of these gravity waves, and the setup that was used to detect them was essentially laser source, split into two parts, two equal lengths, and this laser goes out, and if there is no disturbance of any kind, you will receive identical signals on both these ends, modulo the noise. But once this gravity wave passes, it stretches and pulls the space-time. So then the signals see the difference. The light signals see the difference, and this gets captured, and this can be compared to the gravity waves coming out of a black hole merger, and they match exactly. However, this is all classical, but we know that to understand gravity, we should understand it quantum mechanically. And so the questions that we are asking in this project is, what are the quantum mechanical signatures of black holes? If we understand that, we will understand also quantum signatures in these gravity waves. And it will teach us definitely something more about aspects of black holes, which classical description misses. So we approach this problem from the quantum side. So we take two high energy particles and then we make it scatter. And then they can come very close to each other. And if they come too close to each other, we expect they will form a black hole because everything gravitates. So whether they form a black hole or not, this depends on two parameters: the energy of this process and the separation between them. So it is in this space that we want to understand where the black holes are located. And we expect that when the separation is small, energy is large, we will have more and more black holes. And what we demand from our quantum mechanical calculation is that it is a sensible calculation, that what comes out of it are probability distributions, and probabilities are chances of things happening. So if you add up all the chances, you should get one. So that is one demand we make. We scatter identical particles. So we exchange two particles, then the probability should not change, or it should change in a very predictable way. We put in that, and we put in the fact that if these two particles, massive particles, are interacting very far away, from far away distances, we should get usual Newton's laws of gravity. So we plug these things into a machine which optimizes all these constraints, optimizes this probability distribution based on all these constraints. And what comes out of this are these structures. So this is in the plane of energy of scattering, and J, which is spin of the particle that is exchanged, or the spin of the particles that can be present. And this you can think of in the same way as the separation between the two particles that were colliding, in the same way. And we notice three very specific features. One feature is that there is a band which forms here, which is at very low spin and large energies. This band starts growing. And remarkably, the envelope of this band follows predictions of Einstein's theory of GR. In fact, Einstein's theory of GR, where there is a black hole. So we did not put in black hole, we just put in some expectations of scattering, and then we got out black holes. And then there are these high spin, these structures, these ridges, where there should be something, where there should be quantum states. And then there is these gaps. So what we have, finally, a prediction for a quantum theory of gravity, which can have black holes, is that there is a band of black holes. There are ridges, these high spin ridges, and then there's a gap. And this is a starting step to consistent theories of quantum gravity, where these structures must be present in some form. So for more details, keep an eye out from research from our collaboration. And we are very thankful to ANRF for giving us this opportunity.